In this video, we're going to be just continuing on with permutations and specifically looking at the more advanced cases. So let's just recap really quickly. So permutations, we have to figure out how many different ways there are to order the set. The most basic ones are we've got the whole set, we're permuting the whole thing. That's just the number of the things in the set, factorial. The second level of complications are if we're permuting the whole set, but we can't tell the difference of stuff, certain things within the set. Okay, so here I'm still arranging the entirety of the 7 things, but there are identical things in the set, so I can't tell the difference between some permutations. So I'm going to take my total number and divide out the permutations that I can't tell the difference between. And in this instance, it was 3 factorial, 4 factorial. Then we looked at things where I'm going to permute only a certain number of things from the set. So in this case, I think it was, we had runners here, and I want to know how many different ways there are to finish first, second, and third. So I take my 10, and then I permute 3 from that 10. So to figure out how many different ways there are 10 times 9 times 8 different ways. And then our notation is 10p3, or our notation is 10p3, and we did a couple of examples like that. So let's look at some more intense things. So let's say we've got a website that requires a case-sensitive alphanumeric password with no repetitions, and we can have between 5 and 7 characters. So cases are triggered when you have multiple situations that satisfy the condition, okay? So like if you look at this previous example here, like, if there's 12 songs, we are picking exactly 8 of them. Here, in this case right here, we have, some pool of characters. We're going to we can pick 5 of them, or we can pick 6 of them, or we can pick 7 of them. So these are all linked by or, okay? As soon as you see that or, you're going to think to yourself, ooh, I'm going to be adding, that's addition. So I'm going to be adding those cases together. So let's think about this right here. So it is case-sensitive alphanumeric. So, well, let's start with the alphabet. I've got 26 letters in the alphabet. I actually have 2 sets of 26 because I have the uppercase letters and I have the lowercase letters. That's the alpha part of the alphanumeric. And in addition to the alpha, I have the numeric, which means I have 10 numbers to pick from. And those would be 0, 1, 2, all the way to 9. Okay? So in total, my set that I have to pick from is, 62. So I've got 62 things in total to pick from. And I cannot have a repetition there. It's important for me to note that I cannot have repetition. So let's do case 1. So let's say case 1, the most basic password is 5 characters. So 5 characters. I can't spell word characters. So 5 characters, I'm going to have 62, and I'm going to permute 5 of them. That is case 1. Case 2 is the exact same thing, except now I have 6 characters. So I'm going to say 62p6, and then case 3 would be 62p3. Okay? And it's important to note that, this 62p5 is all the different 5-character passwords. This is all the different 6-character passwords, and this is all the different 7-character passwords. Any of those permutations are acceptable given the constraints of the question. So what I can do then, this is going to be a huge number, so I'm just going to write it as an expression. So all the acceptable passwords are equal to 62p5 plus 62p6 plus 62p. I wrote 3 here, but this should be 7. I think I was thinking case 3. 62p7. These represent all the sum there are all the permutations that satisfy that condition. Those are all the different password combinations out there. I said combination there, all the different password permutations out there. So let's do an example here. So you've got make a playlist of a 12-song album that has between 7 to 9 songs on it. So we're going to say you've got 12p7 plus 12p8 plus 12p9. And then that sum right there works out to all the different ways to make that playlist, assuming that the order is important on that playlist. And because we're in the permutation section, we're going to say it is important. The next one, there's how many different 3-digit numbers. Yeah, how many different even 3-digit numbers can you make? Greater than 300 using the digits 1 to 6. So let's just write those out. I'm going to be using 1, 2, 3, 4, 5, 6. And I have a 3-digit number. Okay. So this is definitely going to be a case question, and I'm going to kind of set it up a little bit differently here because I'm going to think to myself, okay, what are my options? So case one, I'm going to say case one is going to be starting with it has to be greater than 300. So I'm going to say case one, my number starts with 3. So starts with 3. Okay, so if I'm thinking, okay, I've got a 3-digit number here and I'm starting with 3, that means I only have one option for the first number. It is a 3. So I'm just going to put the 1 there to say there's only one option. So this is one option. And then I'm going to think, okay, it has to be an even. So how many options do I have for my last number? And my last number, it can be a 2, it can be a 4, or it can be a 6. So I have 3 options there. 3 options there. And then how many options do I have for the middle number? And there's no repetition, by the way, in the question. So how many options do I have for the middle number? The middle number then can be a 1, can be a 2, 4, 6, whatever one I didn't use, and it can be the 5. So I've got 4 options for the middle number there. Okay. Now you could, if you want to use your permutation notation, you could say that this is going to be 1p1 times, what is that going to be, 6p4? No, I've got, how many options do I have? I've got, 4p4. 4p4 times, and then, excuse me, 3p, 3, oh no, it's 4p1, I'm only picking one. Yeah, I'm only picking one option, 3p1, I'm only picking one option. That's if you want to use your permutation notation. For me, for a question like this, I just like writing it kind of just using a fundamental counting theorem approach, just thinking about how many options I have. Makes it a little bit easier on my brain. So case 2. So starting with 3, make sure, and by the way, I don't have a 0 as an option, so I don't have to worry about like this being 0 and not triggering, it being greater than 300. So let's erase these black marks here because that kind of corresponds to what I was just working on for the first case. So case 2, I start with a 4. Start with 4. Oh, and by the way, I could do these cases all differently, and I'd say 6, 4, and 2. And actually, that might have been easier because now I'm going to have to do 3, 4, 5, and 6. So that's 4 cases versus having just 3 cases. But I'm already in this one, so I might as well do it. So if I start with a 4, again, I only have one option for the first number. And then I am going to once again have 4 options for the middle number. And then I only have 2 options for the last number. And some of you might be asking, well, why do I have only 2 options for the last number? Because I've taken the 4 out of circulation, I only have 2 even numbers to pick from. And then whatever these 2 numbers are, that reduces the middle number by 2 from 6 to 2, or from 6 to 4. Let's go over here and say case 3. Case 3, I'm going to start with 5. And that's going to give me 1 times 4 times 3. Because the 5 is essentially like a 3 in the sense that it's just some random odd number, so it's not going to interfere with that last one there. And then case 4, I'm going to start with a 6, which is going to be, again, just like the 4 there, so 1 times 4 times 2, because 6 is an even number. So this is going to give me 12, this is going to give me 8, this is going to give me 12, and this is going to give me 8. So 8, 8, 12, and 12, so what's that, 24, 32, 40 different ways from adding them all together. And again, I'm adding them all together because cases are an or statement, because it can be case 1, or it can be case 2, or it can be case 4, or it can be case 3. Any of those are valid ways of permuting things. Finally, the last thing I want to talk about is restrictions on the actual arrangement, and these come up in a lot of those photo questions or seating arrangement questions. So let's look at this right here. How many different ways are there for Vision, Wanda, Agatha, and Pietro to take a picture if Vision and Wanda need to be together? So normally in this question, we would just say, hey, I've got 4 things. It's going to be 4 factorial. However, 2 of those things, let's say that's Wanda and Vision, need to be together. So instead of it being 4 factorial, I actually just view Wanda and Vision here as a single entity. Okay, they are a single thing that I'm going to be permuting. So I'm just going to write this as 3 factorial. Okay, so Pietro, WandaVision, and Agatha. It's kind of funny because it's called WandaVision, and look at this. We are literally combining them into one thing when we're doing our factorial. So this represents all the different permutations of those larger groups being rearranged. However, within this group right here, within this WandaVision group, it could either be WandaVision or it could be Vision Wanda. So because of that, I would actually multiply this by 2 factorial. Some of you might just say, why don't I multiply it by 2? That's the exact same as 2 factorial. However, if this was a group of 3 instead of a group of 2, it would be 3 factorial because there's 3 factorial ways of arranging it. There would be 3 factorial ways, just like there is 2 factorial ways of arranging WandaVision. Okay, so let's do another example here. Again, same sort of situation. You got 5 people: Jar Jar, Boba Fett, Jabba, Luke, and Darth Vader. How many different ways of arranging them if Darth has to be in the middle? Well, for this one, I'm actually just going to sketch it out. And for a lot of these, you'll see me kind of making little notes here because it kind of, helps me orient my thinking. So for question 1, if Darth has to be in the middle, I actually only have one option then for here. That's Darth Vader. And then for everyone else, it's 4, 3, 2, and 1. So this is actually a nice, easy one. This is just the same thing as 4 factorial. For question 2, since Darth and Luke must be together, so again, I'll do my little 5 here, just kind of show you what's going on. So you've got your 5, and I have to merge 2 of these into being one thing because Darth and Luke are together. So it's 1, 2, 3, 4 different groups that are being moved around, so 4 factorial. And within this group, there's 2 factorial ways of arranging them. Finally, question 3 is a tricky one, and it's one that comes up a lot and students have trouble with. It's one where you've got a negative situation, a negative condition. So here we're talking about, hey, these 2 cannot be together. So how do you figure out a negative condition? And the answer is we actually treat it like a positive condition. So what we do is we figure out all the ways that Jar Jar and Jabba can be together. And this sounds weird. Basically, you've got like all your sets, or all your permutations, all your perms can basically be either one of 2 things. So your J's are together, that's one set, and your J's are not together. And my J's are Jar Jar and Jabba, not together. Okay. So if I figure out all the ways that they're together, and then I subtract that from all my permutations, then all that's left is the ways that they're not together. So luckily, in part 2, I actually figured out all the ways that 2 people can be together. So 4 factorial, 2 factorial is all the ways that any 2 people can be together. It doesn't matter if it's Boba Fett and Jabba or Luke and Jar Jar. Who cares who the 2 people are? This is all the different ways 2 people can be together with no other restrictions. If I'm having no restrictions in general, and by the way, I'll just make this little note. So no restrictions is literally 5 factorial. Because there's 5 people, there's 5 factorial ways of permuting them. So 5 factorial represents all the possible permutations. 4 factorial, 2 factorial represent all the permutations where any 2 people are together. So if I call those 2 people Jar Jar and, who's the other one? Boba Fett, or is that Jar Jar and Jabba, excuse me. If I say 5 factorial minus the 4 factorial, 2 factorial, this is all the permutations where, in this case, Jar Jar and Jabba were together. If I remove those from all the permutations, in total, then what's left is all the permutations where they weren't together. So whatever that answer is, that is actually my final answer in terms of the numerical value. And that's it for this video, and I hope to see you guys in the next one.